Okay, so we will talk about eigenvalue, eigenvector of a matrix. So, for that we need to just define first what do we mean by characteristics equations of a matrix. Characteristics equation of a matrix. Okay, suppose we have a matrix A, which is Aij's. This is a square matrix, n cross n matrix. So, A has to be a square matrix. We have a square matrix, m cross n cross square matrix. Now, if we consider, and these are coming from a field, and this could be real field, but in general this is a coming from the field F. Now, if you consider the determinant of this, so this is date of A comma x I n. This is a n cross n identity matrix, and if we make it to be 0, this x is a indeterminate, I mean the variable. So, then this will give us a n degree polynomial, and that polynomial is called characteristics polynomial, and if we equate to 0, that will give us a that is called the characteristics equations. So, let us take a what do we mean by this determinant. So, we have a matrix A, A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN. Now, how to get this value, this determinant? This matrix is A minus x of I n is nothing but identity matrix of order n cross n. This is nothing but A 1 1 minus x, remaining will be same, only the diagonal element will change. A 2 1, A 2 2 minus x, A 2 n dot 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 A n 1, A n 2, A n n minus x. This is the corresponding matrix. Now, if you take the determinant of this matrix, determinant of this, that will give us a that will give us a n degree polynomial, and that polynomial is we are denoting by psi a of x. This is nothing but this is a n degree polynomial. This is something c 0 x to the power n plus c 0 is minus 1 to the power n, c 1 x to the power n minus 1 plus c 2 x to the power n minus 2 dot 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 plus c n. Okay. So, this is a polynomial, this is denoting by phi a of x. This is a polynomial of degree n. This is a polynomial of degree n. Okay. And where coefficients are coming from the principal minors. So, where our CR is, so CR is nothing but minus 1 to the power n minus r, sum of the principal minors of the principal minors of A. Principal minors means if we have this, these are the principal minors, the diagonal elements, sum of the principal minors of A of order R. Minors of A of order R. Okay. So, yeah. So, this is the thing. So, what is C 1? So, C 0 is basically minus 1 to the power n, and what is C 1? C 1 if we calculate, C 1 is minus 1 to the power, just r is equal to 1. So, this is n minus 1, and principal minor of order 1. Order 1 means the diagonal element. So, A 1 1 plus A 2 2, just remove this. So, A 1 1 plus A 2 2 direct A n, and these are the trace. This is called trace of a matrix. The sum of diagonal element is called trace of a matrix. So, this is the this, and what is C n? C n is this will become 0 and principal minor of order n, that itself is the determinant of A, date of A. So, this is the this thing, and so this is the coefficient of the characteristics polynomial. Now, if you make the characteristics polynomial to be 0, that is called characteristics equations. So, phi of A x is 0, this is called characteristics equations. Okay. We will take an example how we get this characteristics equation. So, this is a n degree polynomial equations. So, we will take an example, simple example, say we take A is a 2 by 2 matrix, this should be a square matrix 3 5. Now, we want to find the corresponding characteristics equation for this. So, how to get that? So, we have to get the determinant of A minus x 2 cos 2. So, this is nothing but determinant of 2 minus x 1 3 5 minus x. So, this we want to be equate to 0. So, that will give us a phi of A x. Now, what is this? This will give us, so this multiply by this. So, 2 x into 5 x minus 3 equal to 0. Now, if you simplify this, we are getting x square minus 7 x plus 7. So, this is the corresponding polynomial and this is 0. So, this is our characteristics equation corresponding to this matrix. Okay. Now, Cayley-Hamilton theorem is there. So, that is telling every matrix satisfies its characteristics polynomial. That means, you have given a matrix, we have corresponding characteristics equation. So, it is telling this is polynomial in matrix. Okay. So, this is polynomial in matrix. So, this is called a Cayley-Hamilton theorem, C-L-Y-L-E-Y, Cayley-Hamilton theorem. So, what it is telling, every square matrix satisfy its own characteristics equations. Every square matrix satisfies its own characteristics equations. So, that means this phi A of A is 1 as 0. Okay. So, for that example what we have? So, if we have that matrix like this, just now we have seen 2 1 3 5 and the corresponding characteristics equation we got, characteristics polynomial we got is this x cube minus 7 x plus 7. So, now the corresponding, so now this Cayley-Hamilton theorem is telling, so a cube x square 7a plus 7, this has to be 0. So, this is the Cayley-Hamilton theorem. We can verify this if we calculate a square, then if we calculate this value we can easily verify this, but proof is there, we are not going to prove it. So, this is the Cayley-Hamilton theorem. Every square matrix satisfied its own characteristics equations. So, this is the meaning of this. Okay. Now, if we have this, sometimes it will help, it helps us to get the some power of a matrix. So, suppose an inverse of a matrix, suppose we have this. Now, from here how we can get the inverse of this matrix? So, we can just do like this, we can take A common, A minus 7, it is the identity matrix of order 2, we can say just 2. This is equal to, so we take this 2 and this is equal to minus, oh sorry, this is 7, this is 7 into I 2. This is 7. So, if we replace by this matrix, we have to get the identity matrix. Yes. So, this is minus 7 I 2. This is the way. So, that means, if we take this A into 1 by 7 A minus 7 I 2, this is giving us the identity. And we know A into B, if it is identity matrix, then B is the inverse of A. So, that means, this is the inverse of A. So, A inverse is nothing but 1 by 7, sorry, this is 7 into A minus 7 I 2. So, if you calculate it, we will get this matrix like this, 5 by 7 minus 1 by 7 minus 3 by 7 and 2 by 7. So, this is the inverse of this matrix. So, this is the way characteristics the Cayley-Hamilton theorem help us to find the inverse by this way. So, it has another application, we will talk about that to get the power of some matrix. So, we have given a matrix A, how to find A to the power 50 or A to the power 100. So, this type of example. So, use Cayley-Hamilton theorem, Cayley-Hamilton find A to the power 50, where A is some matrix, say 1 1 0 1. It is not identity matrix. If it is identity matrix, 50 is again the identity matrix. Okay. So, how to get the this characteristics polynomial. So, characteristics polynomial 1 minus x 1 0 1 minus x, this is determinant of this is 0. So, this is giving us 1 minus x square is 0. Okay. So, this is telling us this is the x square minus 2 x plus 1 is equal to 0. So, the by Cayley-Hamilton theorem what we have? So, A must satisfy this. So, we must have A square minus 2A plus identity is equal to 0 matrix. This is the 0 matrix. 0 0 0 0, this is the identity matrix. So, you simply write 0 matrix, 2 by 2 0 matrix. Okay. So, we have this. Now, this we can write as A square minus A is equal to A minus I 2. Okay. So, now what we do? We just multiply, keep on multiply A with this. So, if we multiply A with this, so A cube minus A square is equal to A square minus A. So, that is nothing but A square minus A. So, that is nothing but A minus I 2 like this. So, A to the power 4 minus A cube, again we multiply with this, is same as A minus I 2 like this. If we continue like this, A to the power 50 minus A to the power 49 is A minus I 2, same way we are doing. So, now we are going to subtract this two, this all. So, if we add it up, we will get a to the power 50 minus A is equal to how many times? 49 times, 49 A minus I 2. So, from here we can just get a to the power 50 is equal to 50 times A minus 49 I 2. So, this we can easily calculate if we know A. So, this is the way the Cayley-Hamilton theorem will help us to find the some powering of matrix like this. So, this we can have some example in the lecture note. So, now we will define what do we mean by eigenvalue of a matrix. Okay, so we have given a matrix Aij, this is a square matrix. Now we have the corresponding characteristics equation. This is the n degree polynomial equations. Now the solution of this is give us this is the n degree equation. So, it has n values. So, these are each values are giving us the this lambda eigen roots of this equation. So, this is n degree polynomial. So, this is C 0 x to the power n plus C 1 x to the power n minus 1 dot plus C n equal to 0. So, this is the n degree equations. So, it has n roots, maybe some roots are equals. So, if multiplicity is there, but this is our phi a of x. Okay. Now, the roots of this are basically the eigenvalues of this matrix. Roots of A is the eigen values of A. Okay. Now, suppose lambda is a eigen lambda is a root with multiplicity r. So, that means what? That means phi a of x will be written as x minus lambda to the power r some psi, where is not equal to 0. If it is equal to 0, then again lambda will be another root. Okay. So, this means what? So, if we have a, so we know a n degree polynomial having n roots, and we know some formula of the roots, some of the roots are product of the roots, what is this? So, this we know. So, so if we have a polynomial equation like this is a polynomial equation of degree n. Now, if it has a root of alpha 1 alpha to alpha n, so this will be written as some x minus alpha lambda 1 x minus lambda 2 like this, x minus lambda n with some constant. Okay. So, this is the so now if lambda is a root which is coming r times. So, if the r roots lambda is a root which is coming r times and no more times, this is the indication, then lambda is an r fold eigenvalue of A. This is called multiplicity r fold eigenvalue of A. Any root of this is called eigenvalue. But if the lambda is having the character having the multiplicity r of the corresponding this characteristics equation, then it is called r fold eigenvalue of A. Okay. So, now let us take the example how we can find the eigenvalues of a matrix. So, suppose we have a matrix like this 0 minus 1 1 0. This is a real matrix, the elements are coming from real number. So, what is the corresponding characteristics equations? So, this is 0 minus x minus 1 1 0 minus x. So, determinant of this we have to equate to 0, this will give us the so this is nothing but x square plus 1. So, x square plus 1 equal to 0. This is the characteristics equation corresponding to this polynomial. Now, what are the roots of this polynomial, this equation? Roots are x equal to plus minus I is the minus 1 to the power. So, this is the complex number. So, here here these are the eigenvalues. So, lambda 1 equal to I, lambda 2 equal to minus I. Okay, these are not real. So, it is not necessary that every if we have a real polynomial, if you have a real matrix or the field, I mean these are coming from field, here it is real field, then the eigenvalue will be from the same field, that is not necessary. Here our field is the real numbers, but the eigenvalues are the complex number. So, this is one example where the eigenvalues may not be belongs to the same field. Okay. So, but if the A is a symmetric matrix, then it is coming from the same field. So, that is the so if A is a symmetric matrix, suppose A is a n by n real symmetric matrix, then the all eigenvalues are real. Real symmetric matrix means Aij is equal to, so diagonal elements are there. So, what about the elements over here A 1 2, same will be here A 1 2. So, Aij is equal to Aj, and this is true for all I and j, then that is called symmetric matrix, and q symmetric is if it is minus. So, for q symmetric matrix the diagonal elements are 0. Okay, so, this is a symmetric matrix, then the all eigenvalues are real. Values of A are real. So, they are coming from same field, real numbers, all eigenvalues of A are real. Okay. Now, if A is q symmetric matrix, then they are purely imaginary or 0. Anyway, this proof I am not going. So, now we will discuss the product of the eigenvalues and some of the properties of this eigenvalues. So, we know the characteristics equations from where these eigenvalues are coming. This is C 0 x to the power n plus C 1 x to the power n minus 1 C n. This is nothing but determinant of A minus x I n. And this we are, this is the this what is C I? C r we know, C r is minus 1 to the power n minus r. This is the sum of all principal minor of order r. Okay. So, and we have seen C 1 is nothing but minus 1 to the power n minus 1 trace of the matrix, because principal minor of order 1 is the trace of the matrix A 1 or A 2 2 A n n. And what is C n? C n is the determinant of A, that is the principal minor of order n. Okay. Now, if A is non-singular, now we know this so product of the eigenvalues we know. So, if the eigenvalues, if we equate this to 0, then this will give us the eigenvalues. There are n, this is the n degree polynomial. So, it has n roots, either so it could be real or imaginary, but it has n roots. So, these are the roots. So, now the products of the eigenvalues like lambda 1, lambda 2, we know the products of the roots is minus 1 to the power n C n by C 0. This is the formula we know. Now, C n is the determinant of A. Now, if A is non-singular, then the determinant is 0. Sorry, if A is singular, then determinant is 0. If determinant is 0, that means one of these eigenvalue has to be 0. That means one of these. So, if for a non-singular matrix, for a singular matrix, one of the eigenvalues lambda I should be 0, because this product is 0. Product is 0 means one of these lambdas has to be 0. So, this is one observation. Now, for diagonal matrix, if you have a diagonal matrix, then what are the eigenvalues? Now, if you have a diagonal matrix, say D 1 0 0 0 0 D 2 0 0 0 0 0 D n. Suppose this is our A. These are the diagonal element. Now, what is the lambda A x? This is nothing but D 1 x 0 0 0 0 0 determinant of this D 2 x. So, d n x. Now, the corresponding polynomial is d 1 x, d 2 x, d n x, and this we want to become 0 to get the equation. So, so d 1, d 2, d n r will be the eigenvalues. So, for the diagonal element, the eigenvalues are the nothing but the for the diagonal matrix, diagonal elements are nothing but the diagonal the non-zero diagonal element of that matrix. Okay. So, yeah, we will talk about more on eigenvalues and eigenvectors in the next class. Thank you.